Hello and welcome back to Calculus 1, chapter 2.7, section 2.7, actually, on definition of a limit. The book says, I think, precise definition of a limit because so far it was imprecise. I don't know. So we have a definition as it was posed in 1800, middle 1800s. So it's very interesting that all of the important things of calculus were developed, which are derivatives and integrals, before the limit was really mathematically defined well. It was done by mathematician Weierstrass in 1850s. So, yeah, it's possible to do the math without it, but the core of understanding lies in understanding the limit, obviously, because it will be used for both definitions later, you'll see. So, we talked about the idea of approach from two sides, and we said that if you have some kind of a function and you are considering the limit of that function, we approach from the left, which in this case would go up the function, into that point, and then if you approach from the right, you will go down the function and you will get your limit L. So we write limit x goes to a of f of x is equal to this L. So L is the limit, and we see it's a y value, and we don't compute it directly, we approach it from left and right, and we compute infinitely many values around a, and then we infer what the value would be at L. So that's what we did so far. But now we would like to make this official, right? So let's write down the definition that you are responsible for. So we're going to start with assume f of x is defined for all x in some open interval containing a except possibly at a. So we say limit x goes to a of f of x is equal to L, and here's the core: if for any number epsilon larger than 0, there exists number delta larger than 0 such that, and now we have the calculation over here. So f of x minus L is less than epsilon whenever 0 less than x minus a less than delta. So this is the full definition of the limit. They call it precise definition of the limit in the book. And what it does is actually, in this statement here, provides that squeeze from left and the right, which reflects to the squeeze on top and bottom, because a is a fixed point and x is one that creeps up to A, and that's seen here by saying that the difference between X and A is smaller than some very, very small number that you can make as small as you want. And over here, on this epsilon part, epsilon is another very, 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 very small number. So you see that the difference between calculated values and the limit are also getting smaller, smaller. So they're getting smaller together. So sure, you can learn the definition, but the meaning of it is really in the picture that we, well, I had it earlier. So now I'm just going to add these tubes and epsilon and delta and all of that stuff. So we're going to have the same picture as so far. I'm going to pick A somewhere, which is the one that produces L. And here's what we have now. I'm going to draw it's like a sleeve or like a tube, like, you know, like a tube around this L. And this is A minus delta, A plus delta. So the distance in between over here is delta and delta. And we have L plus epsilon, L minus epsilon, making these epsilons over here. So I hope that you see that as the red one pushes in and the blue pushes in, they push to collapse to A. The red and blue would push to collapse also on L, making these epsilon and delta smaller and smaller and smaller, which are the differences between these values. So we would say that the limit of A is L because the squeeze on one squeezes on the other, it collapses onto the other. So no matter how small you make this delta, there will be an epsilon that will be also very, very small so that the blue and red can collapse onto L. We have seen that in our very first lecture in the pick any chart, it doesn't matter. So if you take a look at the delta over here between the red and this one, delta is 0.001, right? So in this case it will be 0.001, and if you look at the epsilon on the bottom is 0.006. So epsilon is 0.006. So you see that extremely small delta produces extremely small epsilon, and as you are making delta smaller, epsilons would be smaller because these numbers will be marching and being closer and closer and closer to 8. So that's what it means. And these epsilon and delta, I mean, those are the Greek letters. I'm not sure if you're familiar with the Greek alphabet, but epsilon is just equivalent to our E, and delta is equivalent to our D from the alphabet. So we have alpha, beta, gamma, delta, right? That's Greek alphabet has 30 characters, and it's some of those characters they look the same, but most of them don't, as the ones we use. So epsilon and delta are two lowercase Greek letters, just like pi and rho and some other ones that you might have run into before. So over here we see that as you squeeze these guys in, right, the y squeezes also in, and everything collapses onto the black line, providing that the limit of a limit as x goes to a of f of x is just L. So that's the first picture. The second picture is the one that shows that there is no limit, because exact opposite happens if you have, let's say, 1 over x. There are many other examples. 1 over x is fine. So what happens in this case as you are looking at 0 value? Well, if you are to draw the red with a delta and then draw the blue with delta on the other side, you see what happens on the y-axis. If you get closer, now you get closer, so let's say you cut delta in half, or you divide it by 10, instead of using 0.1, use 0.01, you see that the y values are jumping apart more and more, right? So in this picture here, as delta gets smaller, epsilon grows. And it actually, in this case, grows without bound. So, no limit, because they don't collapse onto a single y value. The red one will push this way forever, and the blue one would push that way forever, and they will just shoot apart without actually squeezing onto a value. So as I squeeze here, these y values just go apart, which is completely opposite than what we had earlier in a previous picture, where a squeeze on delta provides a squeeze on y, right, on epsilon, and then we'll just get a pre-calculus situation where input is providing a single output. Over here, as you squeeze, these guys just go opposite of each other, and there is no limit in that case. Ta-da! That's it. I hope you're not disappointed. Bye.